The rate at which temperature falls is called the lapse rate. In a uniform atmosphere, this would be a constant value of 1.98 degrees per 1,000 feet of ascent, often rounded up to 2 degrees. Where the temperature is constant through a depth of atmosphere, we describe it as being isothermal. Where the temperature rises with increasing height, we have what is called a temperature inversion. An inversion would typically form at the Earth's surface on a still, clear night in winter, when the ground temperature falls quickly and the air immediately above it cools by conduction. Here's the temperature height graph again. If you remember from the pressure systems lesson, we often get temperature inversions in areas of high pressure. This is where mass descent of air has taken place, resulting in adiabatic warming of a section of the atmosphere. These inversions were called subsidence inversions. Another example of an inversion usually occurs above the tropopause. Here is the temperature profile around that part of the atmosphere. The temperature through the stratosphere shows a steady rise due to the presence of ozone. Ozone absorbs solar radiation and then re-emits heat energy, warming the surrounding atmosphere in the process. Hence, the tropopause is usually one of the coldest points in the atmosphere. Looking at the air temperature near the Earth's surface, usually measured in a Stephenson screen, we see considerable variations both daily and seasonally. The temperature of the air often varies greatly through a 24-hour period. We will look at the main reasons for this in turn. The sun is at its highest at noon, with the maximum incoming solar radiation at that time. However, due to lag, or what's called thermal inertia, the surface of the Earth continues to receive more incoming solar radiation than it gives out. Therefore, the actual maximum air temperature usually occurs some 2 to 3 hours after maximum solar elevation. This effect is greatest over land on a hot summer's day with light winds. Similarly, the minimum temperature time is around an hour to an hour and a half after dawn. Clouds have a big influence on the maximum and minimum temperatures. If you remember from earlier, we said that clouds reflected incoming solar radiation, thereby reducing the insolation. This would reduce the maximum daily temperature. At night, though, the cloud acts in a very different manner. It re-radiates energy back into the layer of air between it and the surface, much like a blanket. This has the effect of making the minimum temperature much warmer than normal. The combined effect is reducing the diurnal variation of the temperature, but the characteristics of the curve are almost the same. Notice how the maximum daytime temperature is lower with cloud cover, and the minimum temperature, occurring just after dawn, is higher with cloud cover. The wind also affects the diurnal variation of the temperature. By day, the effect is to reduce the maximum temperature. This is because turbulent mixing of the lower parts of the atmosphere brings down cooler air from above, mixing it with warmer air near the surface. Wind also reduces the time that air is spent in touch with the ground, lowering the amount of warming that takes place by conduction. At night, the wind holds the temperature up, preventing it falling as low as it otherwise would. Air near the surface cools first by conduction with the ground. Look at how turbulent mixing then brings the warmer, unaffected air down from a higher level, averaging out the temperature through an appreciable depth of the atmosphere. The direction, as well as the speed of the wind, has an effect on the temperature. This is mainly a product of the surface over which air is moving. If wind is blowing from sea to land, or vice versa, the effect on the temperature will depend on the time of day. At night, an onshore breeze will tend to hold the temperature higher because the sea takes longer to cool down and will generally be warmer than the land. Conversely, through the day, a sea breeze will keep the temperature down because the sea takes longer to warm up. We'll examine local winds at a later stage in more detail. There is, of course, a large temperature variation across the surface of the Earth. There are many factors involved with this, and we shall now take a look at the main ones. Take a look at this diagram. You should be able to see that when considering a unit cross-section of energy from the Sun, the same amount of energy is spread across a greater area at higher latitudes than at the equator. Therefore, any single point at high latitude will receive less energy from the Sun than a point at lower latitude. It is interesting to note that compared to the distance between the Sun and the Earth, the slightly greater distance between the poles and the Sun, compared to the equator and the Sun, is negligible. Each year, on March 21st and September 21st, the Sun is directly over the equator. These occasions are known as the vernal and autumnal equinoxes. On June the 21st, the Sun is directly over the Tropic of Cancer, and the Northern Hemisphere enjoys its summer season. Similarly, on December the 21st, the Sun lies directly over the Tropic of Capricorn, and the Southern Hemisphere is in its summer season. As you can see, this affects the amount of radiation reaching the Earth's surface, and so has a direct effect on the temperature in the lowest layers of the atmosphere. The sea surface temperature takes a long time to react in terms of warming and cooling. Here we see the fact that there is very little diurnal temperature variation of the sea when compared to the land. Look at how the variation over the sea is different to that over land. This is because the sea has a large specific heat capacity. This means that the sea requires more energy to raise the temperature by 1 degree than the land does. This differential of the temperatures over land compared to sea is the cause of such things as sea breezes, where air is coming from the sea to the land, and land breezes, where air is coming from the land to the sea. The origin of the air mass is an important factor when considering temperature. When air is static over a region for a period of time, it gathers the properties of the underlying surface. We look at this in detail later on in the air mass lesson. But it is enough to say at this point that air coming from tropical areas will raise the temperature, whereas air coming from polar areas will lower the temperature. The topography of the land has a major influence on the temperature of the air. At night, air in the bottom of the valley tends to remain rather static due to the sheltering effects of surrounding higher ground. This air, therefore, has the opportunity to cool. Colder air also tends to drain towards the low-lying areas. This is why fog tends to form in valley bottoms on still, clear nights. Here we see the situation on a typical day. It is different from nighttime, as you can tell. Hilltops tend to be cooler than lower-lying areas during the daytime. This is because air comes in from the sides and has little contact with the ground, and hence little opportunity to warm up by conduction. There are also many other effects the topography can have on temperature, such as valley winds and the Föhn effect. But we shall look at these in detail, along with the sea and land breeze, in the lesson on winds. As you can see, there are many important factors about temperature which affect aviation. The principal one is how the temperature relates to the icing risk for aircraft, and we look at that in detail in the lesson on icing. Through this lesson, we have looked at how the atmosphere is heated by terrestrial radiation, including conduction, convection, latent heat, and advection. Also, the idea of lapse rates, and how temperature usually falls with height through the troposphere.